what can we figure out about this circuit? So note a few things. This circuit has a 9-volt battery, indicated by these lines like this. Notice how the positive side is the longer line and the negative side is the shorter line, and it's telling us that it's a 9-volt battery. You know what a 9-volt battery looks like? It's those rectangular batteries. This is hooked up to a circuit that contains a 3 kiloohm resistor. So remember, ohms are our units of resistance, and this is a 3 kiloohm resistor, which means it's 3,000 ohms of resistance. This could be anything. This could be a resistor, like an actual resistor. It could be a light bulb. It could be any sort of appliance or anything that's running on this 9-volt battery. It could be a motor. It could be anything. We don't really care about what it is because we're going to try to find out sort of what this circuit, what happens inside this circuit. So can we figure out anything here? And first of all, let's think about this. If this is the positive side here, this is the negative side, what direction will the flow of electrons be? Think back. What charge does an electron have? We know they're negatively charged. So where are they going to be attracted? Opposites attract, so they're going to be attracted to the positive side. So the electrons actually flow in that direction towards the positive side of the battery. And so basically, they're going to make their way from here around the circuit. Now, we also know that there is something called conventional current. I don't know if you remember this, but conventional current, so our I, actually points to the negative side of the battery. So it goes opposite the direction of the flow. So our electrons flow towards the positive side, and our current is defined as going to the negative side. So can we actually figure out what this current is in this circuit? Well, first we have to make a few assumptions. We have this 3,000 ohm resistor here, but what is the resistance of the wire? And to make all our calculations easy in this course, we're going to assume all wires have a resistance of 0. So basically 0 ohms, 0 ohms, they don't have any resistance. Also, the battery we're going to assume doesn't have any resistance. In real life, batteries actually do contain resistance or do add resistance to a circuit, but in this case, we're going to assume that they don't. So really, the only resistance we have in the circuit comes from the resistor. So if we wanted to figure out what the current was in the circuit, think about what we have. We have that the electric potential difference is 9 volts, because we're given that's the battery. We are given that the resistance of the circuit, because the only resistor, is 3,000 ohms. Can we figure out our current from this? And if you look at your formula sheets and look at one of the most important equations we're going to do in this course, we know that there's a relationship between these things. We're trying to find I. That's what we're trying to find. There's a relationship between these 3 variables, and it's called Ohm's law. And you might remember it as R equals V over I, or I equals V over R. That's the one we're actually going to use here. I is just equal to V over R. So current is equal to electric potential difference over resistance. So when we do this, our electric potential is 9 volts. Our resistance is 3,000 ohms. And when we divide, 9 divided by 3,000, 9 divided by 3,000 is 0.003 amps. So that's our current in our circuit. So if we have a simple circuit like this where we just have one resistor and we know the voltage, we can always find the amps or the current in that circuit. So what about if we skip down to this next problem? What's different about this current, or this circuit I should say? Well, you notice it doesn't just have one resistor anymore. It's got 2 resistors. One of them is a 20 ohm resistor and one of them is a 40 ohm resistor. Also notice here how we have a battery. This time that's a 120 volt battery. That is a lot of volts for a battery. And remember, this side is the positive side and this side is the negative side. The negative side is the short side. So first of all, I always like to think about what direction are the electrons going to flow. We know they flow to the positive side, and we know our conventional current goes to the negative side. So that's the direction that the electrons are going to flow, and the current is. So the electrons are going to sort of make their way around this. Now, what do you think is going to happen now that there's 2 resistors in a row? remember what resistors do. They actually prevent electrons from flowing easily, right? So they're actually preventing the flow from being nice and smooth along this path. And it's actually quite easy. The first question here is asking us to find the total resistance of the circuit. And what that means is, what can we look at these two resistors as if we combine them sort of into one resistor? And it's actually very simple. The resistance, the total resistance of a circuit, so RT, is just going to be equal to R1 plus R2, if we call this R1 and this R2. So it's just the sum of the resistors in the circuit when the resistors are in a row like this, because it's basically got to make its way through both of those resistors. So it's like almost like you can treat those as one resistor, which is going to be a 60 ohm resistor. So it's almost as if this circuit is equivalent, if we sort of forget about these two resistors here, it's equivalent to a circuit, and let me draw this same battery here. It's equivalent to a circuit with a 120 volt battery and a 60 ohm resistor. These two circuits are essentially equal in terms of the flow of electrons through the circuit. It's just as easy for it to go through 60 ohm resistor as a 20 ohm and a 40 ohm resistor. So now that we know the total resistance through the circuit, we can do the same process we did in the previous one, right? Remember, we found the current in the circuit is just I equals V over R. And we can do the same thing here. So the current is just equal to the electric potential over the resistance, and that's going to be the total resistance for the circuit. And the voltage here is 120, and the resistance we said was 60 ohms. This comes out to 2 amps. So this is a pretty big current, actually. This would give you a nice shock. Okay, so that's the current through that. So it's basically, there's 2 amps worth of electrons flowing through here. Or we can think about it, remember an amp is a coulomb per second. So there's 2 coulombs every second passing a point. So if you pick this point here, 2 coulombs are passing this point at any second, and 2 coulombs are passing this point at any second, etc. The next thing we're asked to find is, so let me just check off. We found the total resistance, we found the current through the circuit, which was 2 amps. And I'm going to actually label this here, equals 2 amps. And we need to find now the voltage drop for each resistor, because there's a current going through each resistor, and there is a resistance value for each resistor. So we should be able to figure out the voltage drop, because remember what voltage is. Voltage is like the push on the electrons, right? So each coulomb has a sort of a force applied to it, and the battery is the thing that pushes those electrons through. The resistors, you can think of them as removing some of that energy. So it's slowing them down. So these 2 resistors take energy away from that push that the battery is providing. Okay? So if we think about it, if we look at resistor 1, I'm just going to do this up here in this area. So if we look at resistor 1, to find the voltage drop for that resistor, we can again go back up to our good friend here, Ohm's law, and voltage is equal to I times R. And in this case, for resistor 1, it's going to be the current we know is going to be, well, it's the same current that's everywhere in the circuit. It's 2 amps. And we know the resistance is 20 ohms. So if we do 20 ohms times 2 amps, our voltage across this resistor is 40 volts. So what that tells us is basically this resistor removes 40 joules of energy for every coulomb. Again, the battery is adding 120 joules of energy for every coulomb. This resistor is removing 40 of those joules. It's like taking them away. If you think about it sort of like gravity, right? So it's like this battery boosts up the electrons to a higher level, and then this sort of brings it back down by 40 volts. So that's for our resistor 1. Let's do the same thing for resistor 2. V equals IR. So it's going to be 2 amps again, because 2 amps is everywhere in this circuit, times 40 ohms. And we can calculate this as 40 times, this is 80 volts. That's lost due to this resistor. So what you might realize, and this is more voltage or more energy is lost in this resistor than in this resistor. And that makes sense because there's more resistance here. So it's going to take away more of the energy for the circuit. Now, do you notice anything about these two numbers? Maybe compared to this number here. What do you notice? If you add up those two voltages from the resistors, 40 volts plus 80 volts, you get 120 volts. So if you think about it, the amount of voltage that's taken away by each of the resistors is the same amount as the total energy that's added by the battery. So the battery adds 120 volts, and the resistors take away 120 volts. And actually, that is a law, that the total amount of voltage drops and gains in a circuit must equal zero, or they must be equal to each other. The losses and the gains must be equal to each other. So they basically cancel each other out. And we actually call that law, we call that Kirchhoff's voltage law. And I think I'm actually pronouncing his name wrong, but it's something like that, Kirchhoff. So the voltage law states the total voltage gains must equal the total voltage loss. In a closed circuit. Another way of putting this is that the sum of all the voltages must be equal to zero. You can think of, again, you can think of the battery as providing a positive voltage and these two as providing a negative voltage. Okay, taking that away. Either way, this is a good way to check your work when you get to the end of a question like this, because we could very easily check, do these voltages of the resistors add up to the voltage of the battery? In this case, they do, so we've done the work correctly. So that's what the last question says. What do you notice about the total voltage drop? Well, the answer is it equals the total voltage gained by the battery. And lastly, I'll let you summarize in your words how to find the equivalent resistance in a series circuit. So one more thing, what a series circuit is. A series circuit just means everything in the circuit follows along one path. So there's no branching paths, there's nothing complicated about it, just everything is sort of in line with each other. We call that a series circuit. The next lesson is going to be about more complicated circuits and parallel circuits. So what I want you to do is I want you to try the practice problems here, these two problems. So follow the same sort of processes that we followed for the previous question. One little difference in this question is that for this, we have a different symbol instead of a battery. The little wavy thing means this is actually a AC power source, or an alternating current power source, and the current is at 10 volts. The calculations are no different. So even though, remember, for a AC current, we know that the electrons are sort of going to be wiggling back and forth, if you remember. It doesn't actually change any of the calculations for the resistance or the current in the circuit. Okay? So give these two questions a try. The answers to this one are right here, and the answers to this one we'll take up in class tomorrow.